if we know about how the soil is able to hold and provide water for those plants. So water is needed for plant growth. Water is the medium that plants use for nutrient uptake. Water is the medium for all chemical reactions in soil. So transformations of nutrients, availability of nutrients, also will be conditioned by water. All soil chemistry is happening in aqueous environment. It's in the interface between the solid phase and the solution phase. The solution phase, the soil solution, is what is the plants, where the plants take their nutrients. The plants will not take the nutrients from solids. The plants will take the nutrients from the soil solution. And these nutrients need to interchange between the solid phase and the solution phase. This chemistry, we will look at it next lecture, where we talk about soil chemistry, okay? Water can be a way of destroying your soil at the same time. There's a lot of hazards related to water. The first hazard is the water quality. If your water has contaminants, in Oman especially, salinity is one of the main contaminants of water. If you have bad water quality with high salinity, you may get that you destroy your soil through the use of water. But also, if you overuse water, you can have erosion. You can lose soil because the water can be a carrier and remove those particles that are creating soil fertility. So you may have this type of landscapes where you have gullies and erosion happening. So managing water is one of the most important factors. Before you manage nutrient, before you manage soil fertility, organic matter in soils, you need to think about correctly managing water and understanding how your soils are behaving with respect to water management. So to start talking about how water behaves in soil, we will come back to the basics. What is special about water molecules? What is special about water molecules? Again? Very good. What else? How this is arranged? You have seen the arrangement here on the picture.
V-shape.
Yeah, this V-shape, the 105 angle, what does it cause? What is the property of water that is a consequence? Polarity. Yeah, this is what's called the polarity. So you see that you have one side of the water molecule which has a negative charge, and the other two hydrogens will be more positive. So this imbalance on the water molecule, this causes the polarity of water. Why polarity? Because it has poles, positive and negative poles. And if it's positive on one side and negative on the other side, it may be attracted, the positive to the negative to the positive, and therefore water can have interactions with itself. Cohesion. Cohesion is the water molecules interacting with other water molecules. Water holds water. One water molecule is electrostatically attracted to other water molecule. It's called hydrogen bonds. Hydrogen bonds. So this gives room for two phenomena that we have with water. One is adhesion, that water is binding to surfaces, to other materials. Anything that has a charge will be hydrophilic. It means it's attracting water. If you have something that does not have a charge, hydrophobic, it repels water. The water will bind to surfaces, to other materials, and this is called adhesion. Adhesion like glue, adhesive. It's sticking to surfaces. And the water will also have cohesion, where it's binding with itself. It's just attracting other water molecules. So if one water molecule is attracted to a surface, then it attracts other water molecules and so on and so forth. So water is having a behavior where it is transmitting the energy of attraction with the surface with other chains of water molecules in the medium. So here is an example of water being attached and hydrating a surface of a kaolinite clay. Yeah, a clay in the soil, which we'll talk next lecture about soil chemistry and in the interface between the solids and liquids. Water here is being attracted for the surface of the kaolinite. So the cohesion of water gives rise to this property of surface tension. Yeah, surface tension of water. Water is holding itself. If there is no other things that the water will be attracted to, it's only holding other water molecules and creates this surface tension, yeah, where there is a film of water, which there is an impediment for you to break through this film of water. There is some energy in the surface of the water. And here you can be exemplified. Here some insects are floating in the surface of water because they are too light and they cannot break in this surface tension of the water, so they can just stay there on top of the water film. This phenomena is becoming more and more important the smaller you get. Yeah, if you are a bacteria, the water is extremely viscous, surface tension is extremely important. If you are bigger and bigger organisms, this phenomena is more and more diluted. But as we are looking in soil movement, the water movement in soils, we're thinking about the size of pores. The pores are very, very small. In the behavior of water, this type of properties of the water plays a big role, yeah, in the behavior in soil. So this gives rise to a phenomena we call in soils capillarity. How many of you heard about capillarity? Okay, capillarity. Okay, so capillarity means that if you have surfaces that are close together, like for example, a tube like this, yeah, a tube. If you put that tube in contact with water, because of adhesion, because of the energy of interaction between the water and the walls of this tube, the water is able to climb in this tube against gravity. There is the energy and water is rising inside this tube. If you just place a tube inside the water, water will climb inside the tube. And how high it will rise is the energy of this adhesion between the water and the walls. The smaller the tube, the higher the rise. This is just a phenomena between the water and in small pores or small tubes, interaction between water and surfaces. Now, if you go to the soil here on the side, this is immediately transferred, okay? It means that if you have small pores, it would behave like fine tubes. The water has more capillarity. There's more energy in which the water can be attracted and move through these pores just by difference in concentration. If you have dry pores on one side and wet pores on the other side, the water will move through these pores just by capillarity, just by the interaction between water and the surfaces of these pores. And the phenomena follows this same behavior that we see in tubes. The bigger the pores, the less the energy that these pores will be able to take this water. Yeah, this is reflected in what we call the matrix potential of water. The matrix potential of the water in the soil is actually a function of the size of the pores. If you have bigger pores, you will have that there is less capillarity. If you have smaller pores, you have more capillarity. This part is clear? So the curve here you see on the right, it's important for you to understand for even for the exam. This will be exam question for you guys. You do this on the lab also. Have you done this capillary rise on the lab already? Not yet, you know? But you will do this on the lab. You will see capillary rise also in one of the labs. So how is the capillary rise? You can have columns of soil of different texture. You can place it in the water and see how the wet front is moving up, okay? So with sand, it will move, this is time in days, okay? With sand, it will move very quickly, but not very high. It will rise inside the sand very quickly, but will not reach a very, it will be not very high, the wet front, because sand will be like this, and like this tube here on the right, there's low capillarity in sand. The pores are big. If you have a loam soil or a clay loam soil, the pores will be like this, very small. Therefore, it will behave like small tubes like this and will suck the water higher, but slower. It will be higher, but it will be in a slower pace. This is the speed in which the water moves is another concept that we will introduce in a little bit, which is called hydraulic conductivity. In this environment, you have low hydraulic conductivity. It means the water moves slowly, but you have high capillarity. It means it can be taken long distance just by the difference in the energy of the water and that interaction between the water and the surfaces. Okay? This one is clear?
Can you repeat
Here. Sand will rise very quickly through the pores. The water will rise very quickly to the pores of sand, but will not go very high. Yeah? Because the sand will have big pores. Therefore, big pores will have low capillarity, similar to the big tubes that you have here on the right. The smaller the pores, the higher the rise of the water. Imagine you have water table and you have a wet front from that water table. If it's a sandy soil, that wet front will be not very high. But if it's a loamy soil with fine pores, you will have a much bigger wet front. So the water will rise quicker. But if you just place a dry soil there, who will rise quicker will be sand. The speed will be, sand will be the one that rises first, but it will not reach very high level. So sand has a high ability of conducting water. Hydraulic conductivity, the speed in which the water moves is very high, but there is very low capillarity on the other hand. Okay? So what do you want from a soil? You want both things. You want big pores that will be able to conduct water quickly, but also you need small pores that will be able to retain water in high amounts. Yeah?
Doctor, that means clay is more slower and
yeah. Clays, the water will move very slower. Imagine if you have a very heavy soil, if you just add a bucket of water, it will pound. It will not infiltrate. It will take a long time for infiltration if you have a heavy soil. If it's sand, it will infiltrate very quickly. This is reflected in the speed of water movement in the soil, hydraulic conductivity. But the capillarity will be low in sand. Yeah? And this capillarity means because the pores are big and these pores are not able to suck the water, take the water from other pores. Okay? So if you have a water table, for example, if it's a sandy soil, the wet front will be small. If it's a clay or clay loam or loamy soil, it will be larger because of the fine pores. Okay?
larger capillary?
Yeah, the more capillarity, the larger will be the wet front from the water table. Okay? So, if you have a sandy soil, if you add water from a drip irrigation, it will just infiltrate vertically. It will follow gravity. It will move quickly, but there is low capillarity. If you have a loamy soil, it will be like this picture here on the right, where not only it's infiltrating, but it's moving from pore to pore to pore because the other pores are taking by capillarity this water. So it's not only ascending movement, but lateral movement from irrigation also happening. If you have loamy soil, the infiltration rate will be lower, but there is more lateral movement because there's more capillarity on that soil. If you are dripping irrigation, if it's a sandy soil, it will move only downwards. If it's a loamy soil, it will also move sideways because of the capillarity. So capillarity, you want to have some amount of fine pores that will have some capillarity on your soil also. Capillarity, small pores will be also important for water holding capacity, which we'll describe in a bit. So how does water moves in the soil? Physics, yeah? Salam. Water moves in the soil because there is a difference in potential. Yeah? If you drop this glass here, the glass will fall because it has a higher potential here than in this place. There is a difference of potential. Any movement by physics, there is an energy level difference. Yeah? This is gravitational potential. Yeah? Potential energy, gravitational potential. But from the water in soil, there's other types of potential that we need also to describe. So if water is moving, it's moving from high energy to low energy, from high potential to low potential. Think about energy as pressure. If you apply more pressure, the water will move from high pressure to low pressure. Yeah? But inverted in your head, in soils, in dry soils, these potentials are negative, which means that high potential means less negative potentials, and low potential means more negative potentials. Is that easy to follow? Instead of having positive, like you have a pressure in a pipe, you take it the other way around, below zero. High potential means less negative, and low potential means more negatives. Yeah. So it's a suction potential. It's pressure, but it's negative pressure. And why this suction is because there's energy in which water is retained by the soil pores. The pores of the soil are holding the water like a sponge. A sponge will hold water like this image here. In order to remove that water, you need to squeeze that sponge. You need to apply pressure. So the water is being held by the soil. It's a negative, potential, because the water is being held, not pushed, but held by the soil. So this is why the energy potential of the matrix of the soil is negative. Okay, it's a negative potential. So it works like a sponge. Yeah, it's an energy in which is retaining the water in the pores because of adhesion, and you need to apply pressure to move that. Or you need another more negative potential. So the water will move from the higher to the lower, the less negative to the more negative potential. If you have a drier soil, the potential becomes more negative. So it will move from higher to lower potentials. So this is the concept of matrix potentials. Yeah, matrix potentials. You have these are the potentials that you will have in soils. Yeah, you have gravitational potential, you have pressure potential or suction, yeah, and you have osmotic potential. Okay. So gravitational potential is clear. I don't think anybody has a question about this. Gravity is an acceleration that is exerted by mass objects. So any object that has a mass will be suffering the effect of the mass of other objects. And us, we are thinking we are still, but actually we are in an inertia framework. And anything that is falling is non-inertia framework. So gravity is actually just that force that results between the attraction between anything that has a mass. Okay. For the purpose of this course, let's contain like an energy potential. It will be treated like an energy potential. Matrix potential is the potential which is the energy in which the water is held by the pores of the soil. We talked about that in the previous slides. Yeah? How strongly the water is held by the pores of the soil. So submergence potential is the same pressure potential, but when you are below the water level. If you are below the water level, the weight of the water will apply a pressure. The deeper you go below the water table, you have the water table here. The deeper you go, the more pressure you get. Like when you dive in a swimming pool, The deeper you go, you feel more pressure from the water. It's the weight of the water on top of you. The deeper you go, you get more pressure from the water. This is a pressure potential. Yeah. The matrix potential is on the dry side. Yeah. The matrix potential is a negative pressure potential. The matrix potential is when you are in the unsaturated soil up here. Now the water is not pushed around by pressure anymore. It's held by the interaction between the water and the pores of the soil. So the pressure potential and the matrix potential, they are talking about the same things, but one is suction from the pores of the soil, the capillarity of the soil, and the other one is pressure just by the sheer weight of the water column. So below the water table, you get positive pressure potentials, okay? Below the water table, you get positive. When you reach the limit between the water table, the pressure potential becomes zero. There's no pressure, there's no weight of water on top of that point. And if you go up, it's the opposite. They become negative. They become the matrix potential. Now it becomes how much the water is being held by the pores of the soil. So you get here pressure or submersion potentials, and in unsaturated soils you get matrix potentials. When the matrix potential, when the point reaches the surface of the interface between the water table and the unsaturated soil, the Vaudou zone, this is zero matrix potential, zero submergence potential. There is no pressure of the water table, but also there is no suction. This interface here is where it's zero pressure or zero suction, okay? Up on the dry soil, you have more suction. The drier it gets, the more suction you will get. The deeper it goes, the more pressure you will get, okay? So pressure submergence potential is only happening on saturated soil. Matrix potentials is only happening in unsaturated soils where you do not have saturated conditions. The pores are mixed with air and water, not fully occupied by air or water. Now, osmotic potential, you probably heard about this before. Osmotic potential. What is osmotic potential? Yeah? Go ahead. Concentration of something in the water?
Ions.
Ions solutes in the water will change the potential of the water. How does these ions, the salts in the water, will change the potential of the water? It only will change if you have a membrane. And this membrane does not allow the salts to move, only the water. If you have that, you have one membrane, and that membrane allows for the movement of water, but does not allow the movements of salts. The salts, where they are concentrated, will have the behavior as the pores of the soil will have. It will pull the water to those sides. Yeah. So the osmotic potential will be a negative potential that will be pulling the water from where there is more salts. But this will only happen when you have a membrane. Yeah. If you have a membrane, where do you find membranes in soil? Sorry? Where do you find a membrane in soil where the water is going through but the salts are not going through? It's like a filtration membrane. The roots of the plants. Also, microbes. Yeah? Inside the cell of the microbe, outside the cell of the microbe, there is difference in concentration in salts. So this potential is hugely important for the movement of water from the soil into the plant. But between 2 points in the soil, it's not important because they will have the same potential. The salts will equilibrate. Yeah? If you have sodium chloride, you apply in the soil, and another point in the soil, slowly that concentration will balance, will equilibrate over time, because there is nothing impeding that diffusion, okay? But if you have a membrane that impedes the diffusion, like the plant roots, then you have the difference in potential. And maybe the roots are filtering out sodium chloride and absorbing nutrients. But as it filters out the sodium chloride becomes more concentrated outside the roots. And then it's pulling water from inside the roots out. This is, in a nutshell, the problem with soil salinity. The problem with soil salinity, the main one is a problem of water availability. A high concentration of salts in the soil causes drought stress to the plant. The plants become dry because the soil is pulling water from the plant due to the osmotic potential. Okay, is that clear? So if I have 2 points in the soil, there's nothing in between them, osmotic potential will not play a role. It's matrix potential and gravitational potential. Unless you have submergence, if it's below the water table, then the submergence potential will play a role also. But in the dry soil, 2 points, you will only have the role of matrix potential and gravitational potentials. If you have a root or a microbe, then osmotic potential will also play a role. The higher the concentration of the salts, of the solutes, the more negative the osmotic potential will become. So the water will move from the high potential, less negative, to the low potential, more negative. Okay? So it's important for you to make this distinction that not always one thing means the other thing. If you have more water, yeah, it does not mean that there is the difference in moisture concentration not immediately reflects the potentials in the soil, the matrix potentials. The soil water potential reflects the energy level. You could have that in some situations you have difference in texture, and at the same moisture, one soil is very dry, at the same moisture content, let's say 30% moisture content or 20% moisture content. One soil is dry and the other one is wet. How can that be? It means that we have different water potentials in the soil. One is hard to take the water. If you have a clay soil with 20% moisture, that clay soil could be very dry because the pores are so small, they're holding the water with high energy. So there's a negative state, energy state of the water in the soil. Whereas if you have 20% in the sandy soil, that will be very wet. The water is retained with low energy. The plants can take water very easily from that soil. Okay? So water content, we have two ways of measuring water content. One is gravimetric and the other one is volumetric. Gravimetric means the percentage of water in mass basis. Yeah? Mass of the water over mass of the dry soil. So grams of water of grams of dry soil, you get the gravimetric. The volumetric is volume by volume. Yeah? Volume of water by volume of the soil. In the last class, we seen mass-volume relationships. What's it called? The relationship between mass and volume? Density, yeah? The bulk density of the soil reflects how much weight you have per a certain volume of the soil, the bulk density. So if you want to transform the water content by mass basis into volume basis, you just need to multiply it by the bulk density. Because, why does this work? Because the density of the water is 1. So, always you have the same amount of 1 gram of water per 1 cubic centimeter of water. Yeah? But the only thing that will vary will be the density of the soil. So if you just multiply the gravimetric moisture by the bulk density, you get volumetric. Yeah? You get centimeters cube per centimeters cube. Whereas here you have grams per gram. Okay? If it's 0.3, it means 30%. 30%, 30 grams, 0.3 grams per gram. Grams of water per grams of soil. Here, if it's 0.3, means 0.3 cubic centimeters per cubic centimeters. Yeah, you are making a relationship of how much water you have per the mass of the dry soil or per the volume of the soil overall. Is that clear? I can repeat. I will repeat one more time. Gravimetric moisture, it's so easy to do. You take your soil take the fresh weight of your soil, put it on the oven. It will dry. Okay? The difference that you lose in mass is what the water that evaporated. Okay? So that weight of the water you divide by the dry weight of the soil. Then you have maybe 0.3 grams of water per gram of dry soil. This is a percentage ways, means 30% of the mass of the soil, of the dry soil, was water. You can go up and down. If it's wetter, you get more. If it's drier, you get less. Okay? Percentage of the weight. Question for you, why don't we divide here by the fresh weight of the soil? Why are we dividing by the dry weight? Huh? Sorry? Yeah, so the dry weight is constant. Given that you're not changing the density, the dry weight of the soil will not be changing, whereas the fresh weight is changing. The more the moisture, you have more fresh weight. So you need to divide as something that is constant in the soil. In this case, will be a relationship between the mass of the dry soil and the mass of the water. This is gravimetric moisture content. Yeah. For us, it's more useful to work in volumetric moisture content because you can transfer that to water. Yeah? If you have a certain depth of soil, let's say 20 centimeters, and you have 20% of that is water, then you can easily know how much water you have in that volume of soil. But if it's by mass, how do you know how much mass you have there in that first? Depending on the density, it will be more or less, okay? So having this relationship here, volumetric moisture, allows you a better management of irrigation, yeah? Working on volumetric basis is always preferred. But you can transfer from one to another easily. If you have gravimetric, which is easier to measure, you can transform that into volumetric by just multiplying by the bulk density, okay? Clear now? Okay.
Please repeat for the bulk density.
Yeah, bulk density.
What's the relationship between the gravimetric, this, and the bulk density?
Yeah, if you multiply the gravimetric by the bulk density, you get volumetric. You can transform one into another one. The bulk density will be how much grams of soil do you have per volume, okay? How many grams of soil do you have per volume? So how much weight per volume? You can use that to transform. If you have weight per weight, now you can transform now. And that works because the density of the water is 1. So 1 gram of soil, the water also means 1 cubic centimeter of water. Otherwise, you will also have to consider, if it's a different density than 1, then you also have to consider the density of the liquid in this transformation. But because this is always 1, then you only need the bulk density of the soil for this transformation. Multiply by the bulk density, and you get volumetric. If you have volumetric, you want gravimetric, divide by the bulk density, you get gravimetric. This is the relationship that you can...
Because the volume is equal to the mass multiplied by the density.
Yeah. Okay, so how do you measure? We take our wet sample, take the fresh weight, take it to the oven dry. How much weight was lost? Divide that by the dry weight, we get gravimetric, no? So let's see one exercise here, yeah? Moist soil weight, 75. Dry soil weighs 50. 75 minus 50 divided by 50 times 100 to put it in percentage, yeah? If you don't multiply by 100, this will be 0.5. grams per gram. Okay? Grams per gram. If you multiply by 100, you say 50%. But it's the same thing. Okay? Now, let's go for another exercise. You have a container. Weight, the container is 5 grams. The moist weight is the container plus the fresh soil minus the weight of the container, 246. Dry weight of the soil, the weight of the dry soil plus container minus the weight of the container. You get the weight of the dry soil. Then you do the same thing again. Yeah, the weight of the water, 246 minus 164, 82 grams. Easy, easy peasy. So if you divide 82 by the dry weight, oh, here's the difference. Yeah, it's showing 165, where here's showing 164. There's a small mistake here on the slide. Yeah, but just it will be, yeah, similar. Then if you divide that and multiply by 100, you will get the percentage. It's the same formula as before. Now in this exercise, it's only considering that you have the weight of the container also, and you need to subtract that. Okay? Is it clear, this one? So if you have also bulk density data, you can transform that into volumetric. If it's 50% gravimetric, multiply it by 1.3, you get the volumetric content. Yeah. Now there is already, I really don't like the example in these slides. The other slides had a similar problem. 65% volumetric water content. If the soil is completely saturated, it will mean that you have 65% of pores in the soil. It's too high, you see? The example is not a good example because it's showing the number which is not realistic. Yeah, the number is this number, 65% moisture content is not a realistic number. Anyway, so given the example is not good, the calculation is the same calculation you will do. What do you expect to find in volumetric water content? If, yeah, up 20, 30% you will get normally in your soils if it's very high moisture. If it's low moisture, you can get 2%, 3% volumetric moisture content. Okay, so it will range between this, like 2, 3%, and up to 20, 25, 30%. But when it reaches 50%, it's already saturated conditions. It means all the pores are filled with water. The porosity of the soils, we will see in last lecture, the porosity reaches up to about 50, 55%, no? So this is the volume of pores. If it's 50, 55% of pores, if you have all the pores filled with water, this is the maximum moisture content that you will get. If all the pores is full with water. And this example here is giving 65, which is not a good example. Anyway, maybe I didn't revise well the slides before I came here, just taking the slides from the previous years, but it can be said that it is not a realistic example for soils. Now, there is, once you can measure the moisture in the soil, there is a relationship between the water potential in the soils and the moisture content. And you see here, there's these curves that you see on the right. These axes can be flipped. They can be represented in a vertical or horizontal way. But what it's actually saying here is you have water content in one axis, and you have matrix potential on the other axis. Yeah? Matrix potential means how negative is the potential of the water in the soil, how strongly the soil is holding that water in the pores. Yeah? Different textures will have different pore sizes. By having different pore sizes, you have different energy in which the soil is holding the water. And you have different relationships at different water potentials. You have different moisture contents. And this relationship, this curve, is called the soil water characteristic curve. Yeah? Soil water characteristic curve. So this is flipped. You see, this one has moisture on the bottom. This has potential on the top. The next one will flip. You have moisture on the Y and potentials on the X. You see here the potentials can be expressed in different units. My preferred unit that I will ask on the exams is bars, yeah, not kilopascals. I normally use bars. Bars is simpler because 1 bar is approximately 10 meters of water, the pressure of 10 meters of water. So it will be easier for you to have a intuitive understanding of this, okay? So if you have a suction of -1 bar, it means you have like a negative suction of equivalent of the weight of 10 meters of water, but negative, yeah, suction. So let's explain this, yeah? Let's explain this. If you have 0 potential, matrix potential, it means all the pores are filled with water. If you have 0 matrix potentials, all the pores are filled with water. And the saturation here will be different depending on the porosity of different soils. If you have sandy soils, you have lower porosity. So 0 potentials will mean that the porosity is lower here. So here is showing like 25% porosity. All the pores are filled with water, you have 0 matrix potentials. So at 0 here, this is the saturation. All the pores are filled with water. As you dry the soil, you decrease the moisture content and you decrease the potential. And this behavior will show a different curve for each texture. A sandy soil will have a steeper decline, where a clay soil will have a slower decline on this soil water characteristic curve. Yeah? This relationship is important for us because from this relationship we can now calculate what is the available water for plants. How much is the water that is available for plants in the soil. So the concepts that come here and complement this now is field capacity and permanent wilting point. Yeah? Field capacity being the moisture at 0.33, negative 0.33 bars. Yeah? So this moisture here will be the maximum that the soil will hold. In minus 15 bars, yeah, minus 15 bars here will be the point in which the plants will die. Yeah. So between the plants in which the plant will die until the maximum that the soil can retain, that will be the available water for your plants. So the concept here will be field capacity, saturation, and permanent wilting point. Saturation, all the pores are filled with water. But what happens if you fill all the pores with water? You have gravitational potential. The gravity will take some of the water away. After the action of gravity, you have some moisture content remaining on the soil, and that is the field capacity. It means the capacity, the maximum capacity of the soil of holding water after gravity takes some of that away. Yeah? Field capacity is defined, yeah, the definition depending on the book will change if it's depending on the texture, but 0.33 is the measurement more accepted. 0.33 bars is, it's here always in kilopascals. Yeah, this means 0.33 bars is the field capacity, and the permanent wilting point is defined as the water content when the matrix potential reaches minus 15 bars. Okay, minus 15 bars. So the conversion is direct here from this one to another one. Just by 100, yeah? By 100 you get both of them. All right, so imagine that this is your soil particle. The water is being held on this surface. Let me go closer here to the screen. Imagine this is the soil particle, okay? This is the soil particle. The water is held on the surface of the soil particle by adhesion. There is an energy of interaction between the water and the surface. Now, after the surface, the water is being held by another water molecule. But imagine that you are a chain of 10 of us, yeah? I'm holding into the wall, into the door. Now I'm holding hands with some of you, and you are holding hands with somebody else. The further you go, it's easier for you to pull and remove somebody. If you're closer to the door, you're holding with more energy, yeah? But the more you go farther from that door, this energy is reduced. So it's the same thing. The water molecule that's holding only to other water molecules, if they're closer to the surface, they are held with more energy to the surface. Yeah? There's more energy of attraction between here because they are only being held by other water molecules. The further you go, the less the energy. So if you have a pore in the soil, and here's the surface of the solids, the water that is further away from this pore is held with less energy. And the one that is closer to the pore, the particle surface, it's held with more energy. So we have, if you saturate your soil and just leave gravity to act, some of this moisture will be removed only by gravity. And you reach a point where the water does not change anymore. The water content does not change anymore. This point is the field capacity. It's the maximum that the soil can retain. After the gravity takes the excess water away, the moisture that remains, that's what we call field capacity, the maximum water content that the soil can retain. If you continue drying this, because of sunlight, because of evaporation, it reaches a point in which the plants will die. The plants do not have enough negative energy inside the tissue to remove the water because it's held with too much energy by the solids. So it's a fight between how much the plant can take and how much the soil can retain. At minus 15 bars, in minus 15 bars, it's the permanent wilting point. Yeah? The permanent wilting point. And this is the plant available water. Yeah, the plant available water is the difference between the maximum that the soil can retain and the last point in which the plant can still take water. So if you go here, in any of these curves, you can come from what is the moisture here at minus 15? Let's say here is 0.5. What is the moisture at 0.33? 20. Okay, so available water is 15. It's a 5% at the permanent wilting point, 15. And if it's 20% at the field capacity, 20 minus 5, 15, that's my available water. You have 15% of the volume is how much the soil can retain in water available for the plants. And this will change here. If you go for the same thing for clay, maybe you start with 20, and then you end up here at 55, and then you get the difference. You get much more water availability for plants. Yeah? Okay, and depending on the texture, then you get more water holding capacity. For if you have finer texture, you get more capacity of holding water for the plants, and if you have more coarse soil, you have less capacity of the soils of holding water to the plants. So here's the curve that you can find if you have here on the bottom. You will see the texture of the soil. If you have a sandy soil, from sandy to clay, the field capacity will be increasing when you have finer pores. So clay, you have finer pores, you get higher field capacity. And the permanent wilting point will also increase, but the difference will be larger. Yeah? The difference between field capacity and permanent wilting point here will be smaller for sand than it is for loamy soils, will be much larger. This is the relationship how field capacity, permanent wilting point, and available water are changing if you change the texture of the soil. These also exam questions. Yeah, this will be for sure questions on the exam. What's the relationship here between texture and available water for plants? But even it is intuitive. If you think about a sandy soil, the sandy soil can retain less water for the plants. Yeah, can retain less water for the plants. But technically speaking, you need to know that this is the difference between field capacity and permanent wilting point. And how do you define field capacity? It's the water content at the matrix potentials of negative 0.33 bars. And permanent wilting point is defined as the water content at the matrix potentials of minus 15 bars. So also already some exercises here, by texture, field capacity, wilting point, volumetric water content, yeah. And this is just transforming. I will not ask these transformations by depth. Yeah, I think it's overcomplicating. So, but it is here for illustrations anyway. So how much is that equivalent is 7 centimeters per meter, the available water, and 0.8 inches per feet. If you are in US, you might like the units, imperial units. Yeah. There's more exercises here also. That how do you transform if you have gravimetric water potential, bulk density, field capacity, permanent wilting point, and then you can transform that into the depth of water. This depth is important. I will not ask this depth in exams, but this depth of water is how do you calculate for irrigation management. Yeah? You are applying millimeters, which is liters per square meter. So if you understand how much is the capacity of the soil of holding water, this is what you should apply for your soil. If you apply more, it will only drain, yeah, in the soil. So these exercises here I will not ask, but I will ask you how to calculate available water. And I will give you different examples about soils with different field capacity and permanent wilting point, and then you say which ones are, holding more water. Let me check the time. How many slides we have left? This is, yeah, it's good. We can continue. All right. So the water will move from the soil into the plant in the same way the water will move from one point of the soil to another soil. There's a difference in potentials. And the potential inside the plant can also regulate. Yeah. With the addition here that you have the osmotic potential. Between one point in the soil and another point in the soil, you will have gravitational and matrix potentials. When you have the plant, then you have the osmotic potentials playing a role. And the plant will use the osmotic potential for its advantage. It will create more negative osmotic potential inside the plant. The plant produces what it calls osmolytes. It means it produces things, solutes, to reduce the osmotic potential inside the plant cells. And that will cause that the plant can absorb more water because it's becoming more negative potential inside the plant, okay? Root hairs is just structures of the root that increase that area of contact between the root and the soil, yeah? Also, roots, besides the root hairs, will have association with fungi, mycorrhiza, and the mycorrhiza will go and also explore the pores in the soil where the water is retained. So this is some diagrams showing the movement of water from the soil through the cortex of the roots and penetrating the vessels and being uptaken by plants. But one of the most important things here is that the reason why there is a negative potential of water inside the plants is because there is water being lost by the leaves of the plant. The atmosphere has a much more negative potential also. You can say here like outside air will have a minus 100 megapascal here, exemplified, and inside the plant minus 7. So the atmosphere is actively evaporating water from the leaves of the plants, and by doing that it creates more negative potential inside the plants. The plants will have more negative potential because they're losing water. It's like a suction. The evaporation on the leaves are creating negative potential inside the plant, and therefore these negative potentials inside the plants make the water move from the soil to the roots. If the plants are more negative, have more negative potential inside the plant tissue, then now the water will move from the soil into the roots. Yeah, and then from the leaves it goes to the atmosphere, and it's this is how the plants absorb water. Yeah, and they need to keep this flux going because this is the way they can the majority of the water the plant absorbs, they do not use it. Yeah, they do not use it for making their matter. They're just flowing through the plant and evaporating. Yeah, flowing through the plant and evaporating. And this is the way the plant takes the nutrients from the soil also. There is a convective flux of water that is causing a passive uptake of nutrients also. So water management involves sustaining enough moisture in the soil with potentials that are less negative than the ones inside the plant, so the plant can constantly take this water from the soil for its metabolism. And if you do not apply it, of course, you will generate stress. Yeah? If the potentials in the soil become very negative, plants cannot take that water, and therefore there will be stress. So if you just reduce the moisture content, for sure you will see that the plants are not growing well. And yeah, this is showing here the relationship between water quality. Not only because the plants have a membrane, osmotic potential plays a big role. Yeah, and ECE here is electrical conductivity, is a measurement of the salinity of the soil. If the soil has more salts, then it will be that there is more osmotic potential, more negative potentials outside the plant. So the plants will struggle to take water from the soil. If you have salts in the soil, the plants will struggle to uptake water. Some of you in salt-affected soils with me also? Yeah, anyway. But this is the first negative effect of soil salinity, is that it causes drought stress for the plants. If you create a very negative osmotic potential outside the roots, then the roots will struggle to take water. So this threshold value here is the soil salinity level where the plants start having trouble taking some water from the soil. And after you cross this, the plants will be stressed up to a point that they will die. There is a maximum salinity the plants will tolerate in the soil until they cannot take water anymore. Yeah? This is just modeling of, I will not talk about this also because this is part of the research from the previous instructor. He's modeling how the water moves in the soil by regulating the conditions in the potentials in the soil, but I will not talk about this. So this is all about soil water. Most important concepts that you have here is the potentials, the water move in response to difference of potentials, always going from the higher potential to the lowest potential. In unsaturated conditions, you have the matrix and the gravitational potentials. And if you have the plant, then the osmotic potential will also play a role. Yeah? If you have saturated conditions, then you have submergence and you have gravitational potentials. And the relationship, important for you to remember the relationship between moisture and potentials depends on the size of the pores, and therefore this is conditioned by the texture of the soil. The relationship between the moisture and the potentials, this is called the water characteristic curve. This is a function of the size of the pores, and therefore it's different for different textures. The concept of field capacity and permanent wilting point will also be important from this lecture. Field capacity is the maximum the water can retain, the soil can retain, but maximum moisture the soil can retain. Permanent wilting point is the lowest moisture content before the plant dies. Yeah? The plant cannot withstand that low water content anymore. The difference between the two of them is the available water. Yeah? So this available water, again, because the relationship between moisture and potential is different for different texture, the available water will also be changing. All right. This is all for this lecture. You have questions about this? So now let's talk about the exam, okay?